Hello again, and welcome to another review session for your final exam for Calculus 3208. And this time we're looking at some more related rates problems, and we're dealing specifically with related rates that involve changing volumes. So lots of fun here. So let's take a look at what's going to happen. We're going to talk about situations where we have to set up some sort of equation for volume in terms of the type of figure that we're looking at. And then we're going to try and compare rates of change with that, but we may have to use some secondary relationships to get our equations down to just a couple of workable variables. And then we'll try to do some problem solving with those things as we get through it. All right. So here's the first situation that we can look at. Let's say we have, in this situation, a reserve water supply container that's in the shape of an inverted cone. So here's our upside down cone. 10 meters high, and the bottom of it, or the top of it, I guess, since we're inverted now, is 5 meters across. Okay, so water is being drained from a valve in the bottom of the container. So we're leaking water out of the bottom here. And it says, how fast is the water level falling when the surface of the water is 7 meters from the bottom? So they give us two numerical bits of information. They tell us when the surface of the water is 7 meters from the bottom, and if the water is being drained from the container at 5 cubic meters per hour. So those are our two numerical values, and then we're going to look at the equation for the volume of the cone, and it's here. Now, the trick that we're going to have to deal with here is that right there we have this little variable r, and r is a variable that we're not typically or particularly interested in dealing with here, because for this particular problem, all we care about is how fast is the water level falling, which will be our dH over dt. So we want to know about that. And the other variable of interest is right here, the 5 meters cubed per minute, which is the rate of change of volume with respect to time. So we're going to have to deal with that. So we don't want to have anything to do with that silly old radius. So what we have to do is look for a secondary relationship. So some other relationship between h and r that will allow us to write another equation and substitute the variable r away. So we'll do that by looking here on the cone, and what we see is that we actually have a triangle here between the slant height and the radius of the original cone. And we also have another smaller triangle inside there. So right here we have a smaller triangle inside the bigger triangle. And the important thing to notice about those two triangles is that they have all the same angles, of course. So they are similar triangles. Well, at least they should be, not the way I draw them. So what we have there is a couple of similar triangles, and since they're similar, their sides should be proportional. And that allows us to set up a little ratio here. So we're going to say that the radius of the small triangle divided by the height of the small triangle, so the radius being kind of like the base length of that triangle, so that radius divided by that height has to be equal to the 5, which is the radius of the big cone, divided by the height of the big cone, which is 10. So we use that to make a substitution. So let's see how all that works. We'll put this all together and solve this problem once and for all. So we'll start with our original function for volume, which was 1/3 pi r squared times the height. And so we determined that r over h was equal to 5 over 10. And if we want to get rid of r, we're going to rearrange that to say r is 1/2 of h. Now, from there, what we have to do is we have to replace r in our equation over here. So then our equation will have 1/3 of pi times, instead of r, we'll say 1/2 of h squared times h again. So then our volume equation becomes, let's call it pi over 1/3 times 1/2 squared is 12. So pi over 12, and then we're going to have h squared times h, which is h cubed. All right, so now we're ready to tackle the problem. Remembering the two given values we had, the rate of change of the volume here, we said it was leaking out at 5 cubic meters per minute, was it, or hour? Let's take a look back. And it was 5 cubic meters per hour. 5 cubic meters per minute would be pretty fast. So since we're leaking out water here, we're going to say that it's -5 because the actual quantity of water inside that container is decreasing. And we want to figure all that out when the height is 7 meters. So when we're 7 meters from the bottom of the tank for our height. That's what they told us. Okay. So now we're going to have to use implicit differentiation here. So dv by dt is going to be pi over 12 times 3h squared multiplied by the derivative of h, because we need to remember our chain rule here. So dh over dt. All right. So now that we've got all that, what we have to do is we've got to try to put together all this stuff to make it a little bit simpler. So dv over dt now is going to be equal to, let's see, 3h squared is going to give us pi over 4 when I reduce the fraction, times h squared times dh over dt. And so now I've got an h, and I've got a dv over dt, and I have the thing that I'm looking for. So I can fill all that in and hopefully solve the problem. So let's see where that takes us. All right, so we're going to say dv over dt is -5, and that's going to be equal to pi over 4 times h squared, so 7 squared is 49, times dh over dt, which is the monster that we're looking for. So let's see, -5 divided by pi over 4 is going to be -5 times 4 over pi, so we have -20 over, and then we'll divide by 49 as well, so -20 over 49 pi equals dh over dt. And there it is as an exact value. Of course, you could get a decimal approximation for that if you want, and if you're talking about units, that should be in meters per hour. Okay? All right, so there we go. One problem solved. Let's see what else we can do. All righty. The next one says, a spherical balloon is being filled with helium at a rate of 10 centimeters cubed per second. How fast is the radius of the balloon increasing when the radius is 15 centimeters? All righty. Let's see if we can draw a sphere. First of all, that's a fun thing to try. I think usually we just draw a circle, don't we? Maybe. But I remember from way back when I was a youngster that Mr. Dressup said if you put one of these on a circle, it makes it look like a sphere. All right, so now we have a sphere, and we want to find out stuff about its volume and its radius and how they compare. So we'll need the volume equation for a sphere, which is 4/3 of pi r cubed, right? And then we're going to have to differentiate that implicitly. No secondary relationships needed because we only have that extra variable of r there. So multiplying by 3 gives us 4 pi r squared times, of course using chain rule, dr over dt. My r started to become an h, but I'm not going to let that happen. Okay, so we've got dv over dt, 4 pi r squared dr over dt. So we want to know how fast is the radius increasing. If dv over dt is positive 10, we have 4 pi times the radius squared, so that's 15 squared, and we multiply by dr over dt, and that's the thing we're looking for, dr over dt. So we're going to work this out to say dr divided by dt will be equal to 10 divided by 4 pi times 15 squared, which I believe is 225. And we'll plug all that together, and it's not going to be a very big rate of change for that radius at that point. The bigger this balloon gets, the less the radius is, or the slower the radius is going to expand, I expect. So let's see what a calculator will tell us. Okie dokie. So my calculator tells me that this should be a really small number. 0.0003 approximately, and that'll be in centimeters per second. One of the best things, or one of the things I enjoy the most about related rates is to sort of sit back and think about how this would work and try to imagine it. So if you're pumping the same amount of volume, the same amount of air into this balloon every second, the bigger it gets, the less that little bit of air is going to matter. So the rate of change of your radius is going to get smaller and smaller. So we're fairly well along here. That's not going up very much. All right, let's jump along to another example. This time we have a conveyor belt, and it seems to be dumping sand here. Is that what it says? Sand pouring from a conveyor belt forms a conical pile. We got a big cone here, and the base of and the radius of this cone are always equal. Okay, so as the sand pours down, it makes a larger and larger and larger cone as it piles up, but the height of this and the base radius are always the same. So h and r are two things that are equal, and it says at what rate is the pile growing 3 minutes after pouring starts if sand is piling up at 5 cubic meters per minute. Alrighty, let's see if we can do this. So the volume here for a cone is 1/3 pi r squared times the height. Okay, that's good. So we'll differentiate now. Oh, no we won't. We've got to make a substitution to get rid of this variable, but that's an easy one here. So the volume then becomes pi over 3 times r squared becomes h squared, so this is just h cubed. Now we can differentiate, and it's easily done. dv over dt equals pi times h squared, well, that was nice, times dh over dt. Okay, so the things that we need and the things that we have. We need to know, we know this, sorry, we don't know what the height is yet, and we want to find that. Okay, so we had to use a secondary relationship, but we also have to go digging here to see if we can figure out some more quantities. So we know that the sand is piling up at a rate of 0.5 cubic meter per minute, and we want to look at this situation 3 minutes after the pouring starts. So the volume after 3 minutes should be the 0.5 cubic meters per minute multiplied by 3 minutes, and that's 1.5 cubic meters of sand. So if that's the case, we should be able to figure out what that height is that we need, because this equation right here tells us that volume is pi over 3 times the cube of the height. So I'm going to fill in that volume, which is 1.5, and that's equal to pi over 3 times the height cubed. So to figure out what our height is, we're just going to take the cube root of 3 times 1.5 divided by pi, so 4.5 over pi. So let's see, what's that going to be? The cube root of 4.5 over pi, and according to my calculations, it's about 1.13 meters. So after 3 minutes, we have a 1.13 meter high pile of sand. And if that's the case, and we know all that business, then we can figure out the answer to our problem now, because we have 0.5 for dv over dt. I'm using this equation again now, of course. So we have 0.5 equals pi times h squared, so the 1.13 squared, that's approximately equal, excuse me, times dh over dt. So then dh over dt will be equal to 0.5 divided by pi times 1.13 squared. So 0.5 divided by pi times 1.13 squared. And let's see what that gives us. 0.5 divided by pi times the square of 1.13. And we get a whopping 0.125-ish. So we got about 0.125 meters per minute. And that's a similar situation to what we had in the last problem. That the bigger that pile gets, the less the same amount of sand is going to affect the height. So something similar happened in there. Cool stuff. All right, we jump along. Ooh, what's happening here? An ice cube is melting, and it roughly maintains its cubical shape as it melts. The surface area of the cube is decreasing at a rate of 1 centimeter squared per second. How fast is the volume of the cube changing when the length of each edge of the cube is 3 centimeters? Whoa, lots of stuff going on there. The lengths of the edges of the cube and the volume and the surface area, all kinds of neat things. I think I'm going to try to do this in terms of volume and the length of an edge. So let's say each edge of the cube is x centimeters long. So we should know that for a cube, the volume will be, ta-da, x cubed. Alrighty. So let's get a derivative of this then. dv divided by dt is going to be equal to 3x squared times dx over dt. All right. So how fast is the volume of the cube changing when each edge is 3 centimeters? Okay, but the information they give us is not about dx over dt. They tell us how fast the surface area of the cube is changing. So let's take a look at the surface area equation then. So the surface area of this cube, let's just call it A for area. Well, there's 6 faces, and each one will be x squared. Okay, so let's see then. The rate of change of the surface area, dA over dt, will be 12x times dx over, oops, that doesn't look like an x, dx over dt. So we know that we're going to try to figure all this out when the length of each edge is 3 centimeters. We know what the rate of change of the area is, and we want to find the rate of change of the volume. So let's just fill the 3 centimeters for x into each of our equations. So we have dV over dt is going to be equal to 27 times dx over dt. And we know that dA over dt is going to be equal to 36 times dx over dt. Whoops, dx. Having trouble right next to us today, over dt. All right, so we also know that the rate of change of area, dA over dt, is -1. So if I put that in here, so -1 equals 36 times dx over dt, then dx over dt should be equal to -1 over 36. Okay, so we've got that much, and once we know that, we can just fill it in over here, and we'll find our rate of change of volume. So the volume is going to be decreasing at a rate of 27 times -1 over 36. So that gives me -27 over 36, which is a fraction that we should at least reduce. Let's see, 4 times 9 is 36, and 3 times 9 is 27. So let's call that -3/4 of a cubic centimeter per second. So that's how fast the volume of water in that cube is shrinking or disappearing or turning into water instead of liquid or instead of solid ice when the cube has an edge of 3 centimeters. Cool. So lots of different things we did there. We saw a rate of change that related volume and side length, as well as surface area and side length, to get at volume and area together. Neat stuff. Lots of different related rates there. Okay, so here's the your turn problem. Lots of cool things. It's another conical funnel question, so good luck with that. And I'll flip to the solution. Here is the solution to that problem. So hopefully when you work it out, you get it correct. And I'll just highlight some of the key things that we looked at here today. So when we're solving volume problems with related rates, it's pretty much the same as all the other types. All we do is find the mathematical relationship between the variables, and then we often need to use a secondary relationship, as we saw. We differentiate implicitly with respect to time, and then we determine any required yet unknown quantities, and then we just fill the required information into our equation to get the value. And we even saw a cool one where we ended up with 2 equations that we were able to work out certain things from and put them together. Lots of fun. Hope all of your studying is going really well. Good luck on your exams, and if you have any questions, please post them on D2L. Thanks.